All right, yeah, thanks for coming this week. And yeah, I should apologize for canceling the seminar last like the week because my second baby boy it's been exactly a month to give a birth for my side, and I cannot really like control my life completely. So right now, so I had to just cancel. So sorry for that. So today, my like the goal of the conversation are two pieces. So one is so I've been very having very busy moment this February. One reason is of course about the that because of the parenting for sure. But one another reason is that from the Texas State University, I'm also involving to like the create the startup of the like the quantum computing like the company, and the university asked me to execute 20 numbers of interview by March, like the mid of the March. And I also have another like the commitment. So I try to finish all like the interview, like the appointment by today. So I needed to digest 20 like the interviews with each of the workers of the each of the companies, including IonQ, NVIDIA, and so on and so on and so on. So it was very like a precious like the experience for me, how the revenue system really goes with the quantum computing like the community. And the one thing I heard of from the senior researchers in the quantum computing, like the either the startup or big tech, so still it is like the challenging to understand the fundamental algorithms of the quantum computing. So in the procedure of the interview for the especially the CS major, so CS major students are very well like the established with the like the classical computing like the techniques such as how to use the GPU or those kind of things. But when the interview is going like, so please explain the like the Grover algorithm, for example, that today I'd like to talk about, then they kind of just lost what they need to say. So the today's my purpose is two-fourths of the conversation. One is I'd like to introduce the Grover's algorithm. That's one thing could be very useful. So it's very like a simple recipe to iterate. So it's quite simple. But another like the purpose of the sharing the Grover's algorithm is so still we are in the university, so and some of my majority here are students. So I want you to understand the geometric intuition that I actually really have. So for that, like the part, so let me try to share my note first that I already shared. So I assume all of you already saw this note from the announcement this like the morning. So if you didn't get it, let me know. Then I can simply just share the video. And also you can find this from the Discord channel. I also posted it on the Discord channel as well. So I'm not trying to just read like the line by line, but let me just try to summarize what is the Grover's algorithm, and let me share my like the iPad like the notability to write something to like to share my like the I own like the intuition. So this is the one of this is the actually the most like the famous algorithm that like surpassed the like the classical supercomputer. So this is the most like the famous one and the actual best possible like the hybrid algorithm so far which is known. So it is very simple. So the description problem is the following. So we have a suppose there are capital N, which is 2 to the n items, the labeled by bit strings consists of 0 and 1. So we are looking for some subset inside of this guy, inside this car, and we just assume this like the subset. We just call it by the solutions. So it's just a mark. So let us just look at the cardinality. You know what I mean? Because this is a finite subset. So the concept of cardinality is very like clear, just numbers of the elements inside of this finite subset. So the only information about this like the set is given through a so-called the oracle, so that you can query a black box function. So make sure that this is very like the classical like the problem, that this like the function maps each of the bit strings to 0 and 1, and we are saying it mark when it hits reach out to just a 1. So we will simply say it as long as the function value is 1, then x belongs to the set that we are looking for. So classically, so without any like the instruction, so for the iteration procedure, so this big theta means that the order of the denominator and numerators are the same, so that these like the numbers of the queries are required. So let's just assume that this can be proven. But the Grover's algorithm that today we'd like to talk about, so this is one of the like the quantum like the interference, so that we can actually do better, so that the order can be improved in this way. So today we will not try to see how we achieve this like the performance, but let us just look at the recipe. What is the Grover's algorithm for like the having this like the improvement? So it is quite simple. So let us
I
just
have a question.
sure.
Sorry, I stopped you. What
Mhm.
is this notation mean? Theta
Uh,
and over.
Big theta means the following. So this is not as like the big O or small o from numerical analysis. The big theta means the same like the order, same order of between the denominator and numerator. Let me try to thing. Uh, yeah, that's actually a good point. So I just memorized big theta correspond to the same order. So let me just search. Just hang on a sec. Yeah, thanks for the question. So big theta. So yeah, thanks for the question. So this is the asymptotic order. So when we say f of capital N is a big theta of like the g of n means same speed or same order between f and g. So this is the meaning. So in terms of the iteration, so there should be the reference to like compare with this like the inside. So it's just a skip. Just hang on a sec. Uh, so it's like. mm So it's
Uh,
just a quadratic like the speed, I should say. So in the iteration like the procedure, in order to like the converge, so it just takes just a this just a this speed. That's the meaning. Is that answer your question or probably should be clarified further?
so it's like n over m, like constant.
So M is capital M is given, capital M
Uh,
and yeah, thanks for the
n is
question. M is
n
given
should
as
be.
this one, and capital N is given like this.
Uh,
Uh, so yeah, so I also want to clarify this meaning. Yeah, thanks for that question. Uh,
Well, Dr. Lee, do you know big omega notation?
yeah, big O is
No,
I
big omega.
yeah, big
Because,
big O
oh, yeah, yeah, no, there's big O, and like if G is big O of F, then F
is
is big omega of O. It's like the backwards relationship.
yeah.
And if they are both big O of each other, so if G is big
Ah,
O of omega, or big O of F, and F is big O of G, then they're big theta. Like one's kind of like upper bound and one's lower bound. And
uh,
then big theta is just they're both.
that mean N and M are about similar,
Um,
different.
no, it's kind of like saying because you can imagine if M is just one, like if there's only one labeled a solution, then this function would have well, it would have big O of capital N, but
Mm.
also it would have big omega of capital N. Like the lower bound, you would have to like it would at the minimum, it's almost always like that. So then if it has both properties, it's big theta.
Okay. Go ahead. Tell me. I
yeah.
can find it. Yeah.
Uh, Thanks for the clarification. Yeah. So I think Logan's explanation clarifies what this like a big theta means. Yeah, thanks for that. So let me just continue. So the description of the Grover's like the algorithm. So in order to explain it, so the quantum like the
Thank you.
states. So if please just interrupt if you have any like questions or comments to clarify. We can think about it together. This is informal seminar to learn together. So this like the notation of the cat represents just nothing but the vectors in like the Cn vectors in Cn. This is nothing but the linear combination like the notation. And this like the each of the coefficient is the complex value. So the meaning of the probability of the each of the cat vector is represented by the magnitude like the square. And because this is has a probabilistic like the meaning, so that the summation of the norm square should be one. So now we have the quantum state, so that the algorithm of the Grover's one, so that we'd like to prepare the certain quantum state to change it and try to just reach out to this like the performance. So here's the way to do it. So what we prepare is so-called the oracle. So the input we have is this function. So we already have this like the subset. So equivalently speaking, we have this function. We have this function. This is now the given input to generate this algorithm. So this app is given. So what we first do is we prepare so-called a phase oracle. So if we put arbitrarily like the cat vector, just a vector in Cn, then we just multiply by -1 to the f of x, because f of x is in either 1 or -1. So it only just flip the phase. That's the meaning. And f is already given in this like the description. And what we also prepare is so-called the reflection, like the projection. So this has also the intuition, so that for the unit vector, so that we have a cat bra like the notation that makes the matrix, matrix. So if you try to think about the meaning of this expression, say, so if you just put this negative, like the identity matrix to the left-hand side, so R sub u plus I over 2 equals this guy. So this is kind of the midpoint. So this means this is a reflection with respect to this vector u. So if you think about just the R1 like the situation, if this does not clarify, I can just happily just draw a picture with you, so that this just means that, so this is the reflection operator with respect to the direction of u. That's the meaning. So that we want to prepare these two pieces. One is the phase oracle depending on the prescribed function f, and then we have the way to describe the reflection with respect to the chosen vector. Okay, so those two are that's like the ingredients. So if you have any
I think I
questions,
would benefit from seeing a quick sketch as to why that's the reflection.
sure, let us try to see that together. Then let me try to, yeah, thanks for all those like the points so that we can learn together. All right. So now we have our sub u, just this guy. So from this description, so now we have this one. So for like the simplicity, so if I just, of course, this is already given at least in C2 for the like that's a single like a qubit. We know it sits on the C2, but for our like the simplicity, so if you just assume if this is just a real for a moment, okay? So let's just write this as just a U. So this just means um how do I describe this nicely? Let's hang on a sec. Yeah, sorry for the end like the waving, in a sense that I really literally do not really prepare everything thoroughly. So wait, this is understandable. I support the learning seminar. Just hang on. Right. Let me first just try to describe the following. So one like to good into intuition. So if you have how do I describe this? If you have this guy that gives you this one. So I'd like to just realize this as a just a midpoint like the expression. So you have this guy and flip the order in a sense that this just is a scalar. Does that make sense, Abby? Up to
Yeah,
you.
and isn't that scalar one?
No, so I just plug in the arbitrary like the vector v here. So this is curved like notation. This is v. So then
Okay.
let me just change it. Sorry. So let me just change the notation. So if this is confusing. So let me just rewrite. So I also am up to here is okay. So
Oh,
one.
I'm
Mhm.
sorry, I understand what you're saying. You were applying R view to a vector. Okay.
Yeah, then let me just keep going. So we know the meaning of this expression. This is just nothing but the um, how should I say this? So just so so we know the meaning of the inner product. That means the orthogonal projection, right? Orthogonal projection. So we just project down to the direction of the v, and we just look at just so we already take the orthogonal projection with respect to v direction, and just update the coefficient. But still the direction is u. So and this is midpoint, mid vector, I should say, mid vector between this guy and this guy, right? Just add two vectors and just divide by two. That means just a mid vector. So what we are looking for is that we kind of I'd like to draw the reasonable picture, but let me just try. So if this is the direction of u, if this is the direction of u, then what we have is the direction of the v. If this is the case, then what we want to make is like this guy, this guy. So so that if we just try to add them and divide by 2, then we should get this guy. So if I just call this as a left-hand side, so this is the vector of the left-hand side. Does that make sense, Avi? Then what is this like so I'm talking about this guy. So if we add this one with this one, then we should cancel the effect of the vertical like the magnitude, and we need to just make the double of the like the horizontal like the direction, but we divide by 2 so that it just gives this vector. Does that make sense, Abi? This is exactly same as so that we just reflect the coefficient with just multiplying by this guy. So this is the effect. So what we are doing is that if we prepare the vector like the u, then for any like the direction that we'd like to put as an input, then we just create the hyperplane in the like the direction of the u, and then we just reflect, and that's it. Does that make sense, Abu? Or still need to be clarified?
No, I think that's pretty good. Yeah.
All right. And let me just go back. Yeah, thanks for all those like the questions. So I am not really learning it. All right. So let me just go back. And please be suspicious, by the way. So I might make lots of like the errors and mistakes that's possible. All right. So even though I was some intuition, but for checking the detail, I'm not new in this like the area, so I need to learn it. All right. So now we have the intuition regarding this like the operator. So naively speaking, once we prepare the direction U, then this determines the hyperplane to reflect. So that's what we prepare. And we also have the base like the oracle. Those two are the like the ingredients to prepare. Now, based on these two, let us just describe the global one. So the very first one is, so we start from this one. So this like the notation of the zero just means the 1 comma 0 in C2, 1 comma 0 in C2, and this like the notation of taking power just means we have a C to the 2n, and this is just a standard basis, the very first one, that's the meaning. And this H represent the Hadamard gate. This H represent the Hadamard gate. Later, we will have plenty of chance to look at it together. Hadamard gate, which is just some specific like the matrix. So by just acting on this like the vector so that we are able to create this so-called uniform superposition like the state. So just by acting on for this vector, if we just put this like the unitary like the gate, we can create the uniform superposition. So this like the uniform distribution is clear in a sense that for each of the 0 and 1, we create the cat vector, and each of the probabilistic coefficient are the same. So in that sense, this is a uniform like the distribution. So it is clear. And now we prepare this like the cat vector already. We prepare the cat vector here. Is that okay with you? Then we use this for the hyperplane direction to reflect. Then we call this by the diffusion operator. Diffusion means we just want to spread out with respect to this selector vector. That's the meaning. But the reality is just this is reflection. So now we have these two. So the global iteration is just nothing but just putting two unitary like the gates. So we start from just the O sub f. O sub the f just represent this guy. So we just flip the face. Either we keep it. If this f is just a 0, we will not change anything. If this f is 1, we flip the just a face. That's it. So that we first decide depending on f whether or not we flip or just keep it, and then just put the diffusion operator from the uniform superposition like the state. And once we have this G, we just will just iterate to just act by this like the global like the iteration. Simply just that's it. So that once we prepare this like the superposition like the state, then so for the t numbers of the iteration, we just keep adding putting this like the G, and that just gives just a result. That's it. It's very simple. So let me just repeat. Depending on this app, just put this or phase or oracle and put the just a diffusion from this like the state and just repeat. That gives this like a performance. It's pretty much simple. So of course, there should be the justification of several like the pieces in a way that why it achieves this one. But rather than that part, I just wanna give you the like the guideline of this like the note that you can try to look at the detail if you are interested. Number one, so in order to consider such a like the iteration, so every like the stages of the matrix should be so-called the unitary matrix or the unitary gate, so that we need to guarantee that whether or not this is a unitary gate. So that was like the given in this like the node, in a sense that if you compute this like the d square, you can show by using the definition with the algebra that this becomes the identity. So that d and d has an inverse by just d itself. And you can also show that this is Hermitian and unitary, so that this is at least like the unitary. And what is this like the O sub f? So either just identity or negative identity. So this is also unitary like the matrix. So that all like the single pieces are like the unitary matrix, so that G must be unitary matrix as well. So this is a one necessary condition to one need to check. And so this like the detail also matters, but rather than just this like the algebraic part, I just wanna just explain like this part for my today's like the explanation. So this like the curved M is the marked set, and this M is the numbers of the elements inside. So this looks something important for today's like the intuition. So we collect the cat vector from this like the marked set. And then we divide by its like the numbers of the elements with the putting the square root. Because square root makes sense because the probability we need to put the square. And the opposite one, we consider x outside from this curve, like the marked set, and we also put the uniform like the state condition. So called by the like the omega, like the perp. So this is actually key of the observation for my explanation. So let's just look at these two vectors. Now, still we have just a vectors, two vectors. So first, each of the vectors are unit vectors. So it just can be checked directly. So this equals 1, norm square equals 1, norm square equals 1 as well. You can simply just check. And the coefficient condition should be used accordingly to check this is 1. And second, these two are perpendicular. So that if you just investigate the inner product relation, just you can show this is just a 0. So they are perpendicular. So now we have a reasonable like the orthogonal two vectors. So that from linear algebra, it makes sense to talk about the linear subspace generated by these two directions. Is that okay with you? Because we have two unit vectors, so that we can talk about the like the two-dimensional like the plane. So let's call such a like the plane by capital K. Is that okay with you? Capital K. So with this one, you can also check the following. So what we can do is that split like the each of the cat vector. This is an arbitrary cat vector, so that we are able to split. So of course, this is in the inside of this capital K. We are able to split in this manner. So, and you can see this is a relation of the sine square plus cosine square equal 1, so that we can just replace these two coefficients by sine and cosine. For each of the like the unit vectors, each of the unit vectors in capital K. Is it okay with you? So what is astonishing regarding this like the 2D like the plane. So the first like the property, because we should look at the phase oracle with the diffusion operator. So if we just restrict this linear operator to this like a two-dimensional plane, you can see that for this one, it just changes just a negative sign. For the perp, it's just a identity. So we have some reasonable property from linear algebra. This is the first one. So that what we can say is that, so this is already interesting. And so this like the linear operator, like the O sub F is preserved by this linear subspace, capital K. This is one property we can see. And the second property is the following. So that this like the diffusion operator also preserves like the K as well. So what I wanted to say is that if we just act by this omega, then it belongs to K, same for omega top. So we also have this relation. So as long as these two are satisfied, this one and this one, then we can say this G also preserves this 2D plane capital K. This is a guarantee. So what does that mean? So from linear algebra, we can see that the procedure of the iteration, this one, it restricts to the two-dimensional like the subspace. So this Grover like the iteration, if you have any like comments or questions, let me know. So what we describe is that we start from the phase like the oracle, and then we act further by the diffusion operator. Then from the consideration we already observed. So for the mark set, we can just look at these two special vectors, and then we generate the two-dimensional plane say by K. This like the procedure of the iteration, only look at the two-dimensional plane. That's it. And this two-dimensional plane consideration gives some like the better performance rather than the classical computer. So there should be something like the behind, because it is linear algebraic like a way is finding the special like the subspace. So that this is a part I'd like to say something more like the detail, what is actually really happening. So So in order to really explain what is really happening, now I'd like to introduce a geometric perspective, what was really going on behind. Is it okay with you? And rest of the notes are for the like the some of the like the parts are necessary, like the details, and some pieces are some geometry today I'd like to talk about. And I am not assuming you have a geometric background. So for the like the majority of the participant for the seminar, so I'd like to today what explain is the following. So let me first like to give you the slogan, what I want to explain. So what when we learn like the quantum mechanics, so of course the Hilbert space like the axioms are very very important, but usually the geometric like the interpretations are not really like the appreciated in a way that one should appreciate. So what I'd like to say is that the specialty of this like the capital K from the geometric point of view. So let me now, it's time to share my like the iPad screen. So let me share the slogan, what was really happening. So, hang on. And my explanation should be over in 20 minutes. Okay, here we go. So this is something we need to use math. So when we talk about the one qubit, so that this is a replacement of 0 and 1, which was real before, but now we prefer to use these cat vector notation, as you know. And these two are the just the vectors in C2. C2. So this guy is same as a 1, comma 0. This guy is same as a 0, comma 1. That we prefer to call it by the standard like the basis for sure. So what we do is we just look at the unit vectors. Let me call by S, so that if we have this guy, or in mathematics, we also prefer to denote this by norm square of this. So if you identify C2 as like a R4, so this is nothing but a three-dimensional sphere inside of R4. And if you have some like the background in quantum mechanics, this is actually same as SU2 in a way that, so let me just give some like the note here. I would not assume that all of our familiar with these types of the geometry, like the pieces, but I would try to like to repeat this type of the argument. Then later on, this could be quite useful. So this S3 is the element of the Z and omega in C2 rather than R4. Then I can simply require this like the sphere condition. ZZ bar plus omega omega bar equal 1. This is good. So that you can map to SU2 just by putting Z bar, omega, negative omega bar. This condition is just nothing but determinant is 1, SU2. And this is isomorphism as Lie groups. So you can just view whatever you want as long as they are just the same. All right, so now we have a S3 already for describing the one qubits. So unit vectors are used to describe the one qubits. So we have the group action on S3 by S1. So in quantum computing, this is called by the Glover phase. So explicitly, we have the action S1 by S3 in a way that S1 can be written by e to the I theta for each of the elements, and we can act by Z and omega. Of course, it satisfies ZZ bar plus omega bar is 1, as it satisfies the rule of S3. Then it maps to nothing but e to the I theta Z with e to the I theta omega. The interesting part is that it also maps to S3. Because if this is recalled by Z prime and omega prime, then in order to check it still stays on S3, is that we need to check Z prime bar plus omega prime bar must be 1. This is what we need to check. But we require Z prime is e to the I theta Z, omega prime is e to the I theta omega. So this is same as e to the I theta Z times e to the I theta Z bar. Same thing, e to the I theta omega times e to the I theta omega bar. And complex conjugate is ring homomorphism. It preserves by the multiplication so that this becomes e to the negative I theta times z bar. This guy is e to the negative I theta times omega bar. And this, like the multiplication, is just a actually over complex so that you can now say you can flip it. You can flip it. You can kill this single pieces so that this becomes zz bar plus omega bar, which is 1, as we require this condition. So this is very like the nice like the picture. This is a very nice picture so that you can imagine that you start from the three-dimensional sphere and then you rotate by S1. You rotate by S1. This is related to that I need to explain for the Grovers like the iteration. So you rotate by S1, and as long as it rotate by just this S1, then you can take the quotient, meaning that as long as it belongs to the same like the phase, same global phase, we identify them as the same. And this is very surprising result. The same as S2 that we call by the Bloch sphere in quantum computing. So before I go further, I need to explain why I should explain this one to describe the like the quantum circuit. So before I go further, if you search the Hopf vibration, this is what is really happening. So Hopf vibration, so this like the picture is drawn for the three-dimensional sphere, not two-dimensional sphere. Of course, we cannot draw the three-dimensional sphere because this is live in the inside of the R4. But this like the effect of the rotating by S1. This is the group action effect. This is group action effect. So that S3 consists of the all like the group orbits given by S1. And if one just identify all those like the global like the phase, this each of the S1 orbit, that becomes precisely the two-dimensional sphere. This is it we call the Hopf vibration. So S3 quotient out by S1 becomes S2. So this is the geometric or topological structure of the three-dimensional sphere, which is a collection of the one qubit. So this is the reason that we identify the collection of the one qubits as a two-dimensional sphere, but the reality is a three-dimensional sphere with just a global phase effect that we want to ignore. That's the way to describe. Is that okay with you? So far I explained. This is some beautiful like the mathematical like the structure. All right. So now let me just go back. So what we do here is the following. So already this description gives some like the intuition. So what was really happening? What was really happening is the following. So this like the theta, this angle. So we start from those two vectors, these two vectors, and then we just declare, we can talk about the sine theta and cosine theta. And what we saw is that we only needed to look at the two-dimensional, like the subspace. Is that okay with you? Two-dimensional subspace for capital K. So what we did, let me just repeat. What we did is we just define two vectors which are perpendicular to each other. And then we generate the two-dimensional plane. We generate a two-dimensional plane. And then we just saw the phase oracle with the diffusion. Those two linear operators are preserved by this like the capital K, two-dimensional plane. But this plane is a vector space. This plane is a vector space, two-dimensional vector space. And we are talking about this two-dimensional vector space over not real, over complex. This is C2. This capital K is vector space isomorphic to C2. So in order to describe the qubit, so as I said, so we collect the like the unit like the vectors. Let me just reshare. So in order to describe the qubits, we collect not just the arbitrary vectors, but we just collect the unit vectors first. That becomes S3. And then we just consider this like the group action, meaning that the effect of the global phase we want to ignore from the whole vibration structure. So once we just identify each of the elements in the same like the S1 like the orbit, then it becomes a Bloch sphere, which is two-dimensional like the sphere. So what is really happening on the like the Grover like the algorithm with that theta is that so the Grover's algorithm is actually just a searching nothing but the two-dimensional Bloch sphere. And we are just rotating this like the Bloch sphere by the radian angle by 2 theta. That's the meaning of this like the Grover's like the iteration. This is astonishing. So what is really doing, let me just repeat, the like the purpose of this like the Grover's like the algorithm, which is one of the best like the well performance, is just nothing but finding the like the rotation of the Bloch sphere. And it's just searching the like the two dimension, so just two-dimensional like a sphere to just rotate. And in each of the procedure, I'm saying each of the procedure mm, of this guy, it's just finding the just a Bloch sphere to just rotate by 2 theta angle with the radian like the unit. So to
And
just
and what we're searching for is W, right? Like
we are
we're hoping.
searching for is W, right?
Yeah. So like the repeated application of G is gonna converge on W.
Right.
Okay. Okay.
So the way to converse to like the omega or W is to just rotate on the like the Bloch sphere with the this angle depending on this like the mark set or whatsoever. To so this is some like the geometry like the figure. That's what I really want to explain. Not just the line by line, like the argument, why this argument works and what was really happening. So the usual explanation from the quantum computer reference is that so diffusion like the operator just behaves to just converge to the like the average in a sense that there's a hyperplane like the axis, and as long as we just repeat this like the diffusion like the acting by diffusion operator, it converges to some like the direction. That's the usual explanation. But I'd like to put some like the geometry like the taste that is really like the rotating the two-dimensional sphere. So with respect to the axis of like the direction of this, like the either the W or omega. So in order to really try to explain, so this is my like the favorite explanation of the what is the Grover's like the iteration. It's the geodesic. It's a geodesic like the rotation in a way that this like the rotating by theta is exactly the shortest path on two-dimensional sphere. So that the Grover's like the iteration is nothing but the geodesic like the just finding the geodesic distance on the Bloch sphere, and we just repeat. So, but in order to explain, I need to explain the geometry like the pieces of all those like the ingredients that today I didn't explain. So in order to really just mathematically justify, I need to introduce differential geometry and what is the concept of the geodesics and so on. But hopefully this might give you some like the intuition. What I'd like to say is, so in differential geometry, this CP1 is same as either S2 or Bloch sphere. It's just the same thing. And then it is exactly the same as just a rotating by 2 theta angle for each of the step of the Grover's like the iteration is not I'm saying the analog is geometrical the same as just looking at the geodesic like the distance. So one like the project that I like the did with the high school student last summer was that so this is still the mathematical modeling of the one qubit. So the modeling of the one qubit just makes the just either the S2 or CP1, But what I did with the high school kid was that with the noisy environment, so this is really not the case. The noisy environment, one need to change the setting of the block sphere to the other things such as a weighted projective line or whatsoever, then that this like Grover's like the iteration should be changed accordingly, for example. Because this mathematical modeling part, as long as you understand this quite well, this has also has sort of the drawback. So like the assumption of the like the block sphere and so on. And but in order to explain that, I need to teach differential geometries for some of the like that's like ingredients. That's the reason. Now let me just go back to the original like the reference that I'd like to cover in this like the reference. So this is the reference that I post for this like the seminar purpose. And in this like the reference, I put the differential geometry like the angle for this reason. So in order to really explain, one should know the basic level of the language of differential geometry to really appreciate what I'm really talking about. So, and I'm very happy to really explain during this seminar. This is not that difficult, in my opinion. It just takes just a few weeks to understand. So this is today I actually really explain with the growers like the iteration. And another like the piece of the like this reference usually quantum company like the textbook or references are not covering is like this like the application that really like the big tech, the quantum computing. I mean, those like the companies are really like caring about, in my personal opinion. So in this like the February, as I said, I have conducted 20 like the interviews with the quantum company, like the startup, like big techs and so on. This is very industrial, like the taste of like the developing the algorithm. I'm not talking about the academic part of the writing the paper. This is related to the like the real like the development of the devices. So in that sense, I try to just cover all those like the pieces, not in a way to just providing the lecture, but more like the project, like the wise way, if you're interested like learning these types of the subject. So let me just finish today's word this way. So usually quantum mechanics and quantum computing lecturers do not like the appreciate differential geometry like the viewpoint and also the FPGA like the processor. So this is what I'd like to cover from this seminar because not I'm not doing this for the lecture purpose, but I'd like to conduct some project by myself. And this is for me to just learn and just like execute some of the like the project by myself. So and if any of you are interested in, we can definitely do something together or learning something together. But it's completely up to the participants as well. But I will just repeat this type of seminar each year in the TXST. So that's so what I want to explain. So if you have any questions or like suggestions or whatsoever, even without the record, I'm happy to listen. So these like the pieces are differential geometry parts, by the way. And so my original purpose of like the posting this like the book was once one covered this like the concepts, then I can initiate to talk about the quantum circuits with this like the perspective. So usually these quantum circuits are just covered with the linear algebra perspective. Each of the unitary gates correspond to unitary like the matrix and so on. But I actually do not like that perspective. I like more like the geometric perspective. This is something like the beneficial, but this is not really needed if you're not caring about geometry.
Actually, I'm not very familiar with differential geometry and quantum feature information.
Mm-hmm.
Maybe you can give a lecture maybe about this kind
I'm
of.
very happy to do it, but yeah, I need to ask the opinion from the participants for sure. And I also assume that each like the Friday we are very like the exhausting, so I do not want to spend like the 2 hours of the lecture. But if any of you like want me to do it, I'm happy to do it because that's my like the specialties on my like the research. So I'm happy to like the give the or like the single pieces of the details for the computation and the intuition and so on. This is not difficult. It's just elementary calculus.
Yeah, so what Rue and I did the last time we met is we worked through it was project set 2 that you put out, which was curvature and geometry on surfaces. So
Mhm.
we computed the metric tensor for some simple surfaces and then the second fundamental form. But I think for both of us that was I mean, it was new, but it was like, I mean, that was quite quick to grasp onto. What we got stuck on is we got to, I'm getting there. I can't remember what the name of this.
Yeah,
The
yeah.
Christoffel symbols, the
Mhm.
notation for that was new, but after a little Googling and a little AI, we figured out the notation. But no, that wasn't too hard to grasp, at least the first and second fundamental form.
Then, yeah, Lou, if you have any like comments or suggestion before I go further.
I'm not gonna lie, it's late. I can't think anymore. I don't have any questions.
So then, probably we can just stop to record this point or this week. Does that mean that we stop the like the seminar right now? But still, I can just stop to record.